Imagine discovering that one of the fundamental symmetries of nature isn't actually a symmetry. For decades, physicists believed that the laws of physics should behave the same way in a mirror. Turn left into right, clockwise into counterclockwise, and the laws of nature should remain unchanged. But one experiment would challenge that assumption. At the center of it was a remarkable physicist, Madame Chien-Shiung Wu. Chien-Shiung Wu was born in 1912 in Jiangsu Province, China. From an early age, she showed an extraordinary talent for mathematics and science. She eventually traveled to the United States to continue her education. At the University of California, Berkeley, she studied nuclear physics under some of the leading scientists of her generation. Her speciality was experimental physics, and she developed a reputation for something scientists desperately need: precision. Wu became an expert in radioactive decay and nuclear physics. She studied the behavior of atomic nuclei and how they transform by emitting particles. But her most important contribution would come from a much deeper question, a question about symmetry. Imagine filming a physical experiment. Now imagine placing that film in front of a mirror. If the laws of physics are symmetric under reflection, the mirrored experiment should obey exactly the same laws. This idea is called parity symmetry. Mathematically, parity corresponds to reversing spatial coordinates. Left becomes right, up remains up, and the direction of motion is reflected. For years, physicists assumed that nature respected this symmetry. But two theoretical physicists began to wonder, what if it didn't? In 1956, physicists Tsung-Dao Lee and Chen-Ning Yang proposed something radical. Perhaps parity conservation had never actually been demonstrated for the weak nuclear force. The weak force is one of the four fundamental interactions of nature. It is responsible for processes such as certain forms of radioactive decay. Lee and Yang suggested that the weak interaction might distinguish between left and right. If that were true, nature itself would have a preference. But a revolutionary idea requires experimental evidence. And this is where Chien-Shiung Wu entered the story. Wu designed an experiment using radioactive cobalt-60 nuclei. The nuclei were cooled to extremely low temperatures and placed in a strong magnetic field. The goal was to align their spins. Then Wu observed the direction in which the emitted electrons traveled during beta decay. If parity were conserved, the electrons should have been emitted symmetrically relative to the direction of the nuclear spin. But that wasn't what Wu observed. The electrons showed a clear preference for one direction. The mirror image of the experiment would behave differently. Parity had been violated. This was astonishing. Nature was not perfectly left-right symmetric. The weak nuclear force could tell the difference between left and right. It was as though the universe had a built-in sense of handedness. For physicists, this was a profound discovery. One of their most cherished assumptions about symmetry had been broken. Wu's experiment provided the crucial experimental evidence for parity violation. Lee and Yang had proposed the idea. Wu demonstrated it in the laboratory. The result fundamentally changed our understanding of the weak interaction, and it helped pave the way toward the modern theory of the electroweak force. In 1957, just 1 year after their proposal, Tsung-Dao Lee and Chen-Ning Yang received the Nobel Prize in Physics for their work on parity violation. But there was a striking omission. The scientist who performed the experiment that confirmed the prediction, Chien-Shiung Wu, did not receive the Nobel Prize. Her omission remains one of the most discussed examples of the recognition gap faced by women in science. But Wu's career was far larger than a single experiment. She became one of the leading experimental nuclear physicists of the 20th century. She worked on the Manhattan Project during the Second World War, contributing to research related to uranium enrichment. Later, she held major academic positions in the United States. At Columbia University, she continued to conduct influential experiments in nuclear and particle physics. Her work helped establish something fundamental about the universe. The laws of nature do not always treat left and right equally. This asymmetry is now built into the standard model of particle physics. The weak interaction is fundamentally chiral. Certain particles interact differently depending on their handedness. Something that once seemed impossible became part of our basic description of nature. And this is what makes Madame Wu's story so extraordinary. She didn't simply perform an experiment. She tested one of the deepest assumptions physicists had about reality. She showed that the universe does not always look the same when viewed in a mirror. So, who was Madame Wu? She was a pioneering experimental physicist, a master of precision, a scientist who helped reveal that nature has a preferred handedness. And perhaps most importantly, she reminded physics of a lesson that science repeatedly teaches us. Never assume nature follows our expectations. Sometimes, the universe is telling us that our most beautiful symmetries are only beautiful because we believed them. Madame Wu looked into the mirror, and nature looked back differently.